Hi guys, Sajjad Hussain again with a new video. In this video, I am going to demonstrate the wind load on an irregular building. For this, I have taken this example number 5 of ASCE 702 guide, but I will not be using ASCE 702, I will use ASCE 716. So here we have to calculate design wind pressure for a typical one-story house are to be determined. Various views of the house are provided in figure 311A through 311D. Physical data are as follows. The location is in Dallas, Texas. Topography is homogeneous. Terrain is suburban. Dimension of the buildings. Dimensions are 80 feet by 40 feet, which is including porch footprint. Porch is 8 feet by 48 feet. Wall eve height is 10 feet. Roof gable angle is 15 degree and overhang is 2 feet all around. Framing, typical timber construction. Wall studs are spaced 16 inch on center. Roof trusses spanning 32 feet are spaced 4 feet on center, and roof panel are 4 feet by 8 feet. Glazing is uniformly distributed. Pressure on component and cladding will depend on the effective area and location. For brevity, all items are not included. And the data is as follows. As per ASCE 702, the wind speed was 90 miles per hour. Importance factor 1. Topographic factor was 1. Directional factor was 0.85. And let me show you the building. This is the plan, elevation, and this is the site. So let me show you the whole building in one picture. So here you can see this is the front elevation, these are the sides, and this is the plan. Gable roof. Now, to define the wind load, we have to take all the possible load combinations, all the wind directions, for example. So here there are 4 directions defined. That means the wind may blow in direction A, the wind may blow in direction B, the wind may blow in direction C, and it may blow in direction D. And because of that, the wind load, say for example, if it is blowing in direction A, so it will be applying pressure on wall or face A, which will be windward. Here wall 5 will also be treated as windward. Wall 3 will be leeward, and wall 2 and 6 and 4, they will be side walls. And these areas like 7, 8, 9, 10, 11, etc., these are the roof areas. And 2 feet overhang is shown all around the building. And this is the porch area. Area number 12 is the porch area. This building is overall 80 feet long, and from this point to this point, that means the width of the veranda is 48 feet, and this side is 32 feet, and the sides are like this, 32 and 8 and 40 feet. So with all this information, I'll show you how to calculate the wind load for this building as per ASCE 716, not ASCE 702. So what I did, I took the same example and generate a MathCAD sheet to calculate the wind load for this building. So here is the reproduction plan, copied the same thing, elevation, side, another side. Now of course, design criteria and etc., load combination, references, etc., same. Now, for the wind load, I took the wind load from ATC website, and from ATC website you can see that as per ASCE 705 the wind was 90 mile per hour, but now for category 2 as per ASCE 16 the wind speed is 105 mile per hour. So I shall be using this 105 mile per hour. The basic wind speed is 105 mile per hour as per ATC. Now, exposure category is B, occupancy 2, importance factor 1, KZT 1, elevation factor 1, velocity as defined, and I shall be using the same formula which is given in the standard. So based on this data I started calculation. So wind load is defined as per ASCE 716 chapter 26. Now we know that the basic wind speed 105, all these parameters repeated over here. The plan is copied just to make it clear that whenever we are talking about direction A, means this will be direction A. Whenever we will be talking about direction B, so this will be direction B. So it's a quick reference, I can say. Instead of going back over there, we can easily see over there that which direction we are talking about and on which surface we are talking about. So all these values are listed over here. Now for value of Kz, refer to table 26.10.1. Now table 26.10.1, I'll show you this is ASCE 716. Let me go to table 26.10.1. So you can see here table 26.10-1, velocity, pressure, exposure coefficients KH and KZ. Building height is 0 to 15 feet and our exposure is B, so the value of KZ will be 0.57. So same value we are using over here, 0.57. KD 0.85, KE is 1 using the formula. So MathCAD calculates the velocity pressure. So QZ comes out to be 13.675 pound per square feet. Up to height 15 feet. And as per section 2611, gust factor is 0.85. And the internal coefficient as per table 26.13-1 is 0.18, of course with plus and minus. Now the very first case is we want to calculate the design wind pressure for moment wind resisting frame system for wind direction A. So for wind direction A, we have to calculate the value of Cp. Now the Cp values are taken from figure 27.3-1. So let me show you from where I am taking these values. Let me show you the figure. So This is the figure 27.3-1 main wind force resisting system part 1 for all heights, external pressure coefficients, CP for enclosed and partially enclosed buildings. This is for wall and roof. Conditions are like this. So if wind is blowing, so perpendicular face will be B and parallel face will be L, and these are the factors which we have to calculate, where CP is given below for gable or hip roof. So here is the value of CP given. Wall pressure coefficient for windward wall, all values 0.85. So I have used this table and I have taken CP from this table even for roof and for the wall. So here for windward wall, CP is 0.85. So windward, as I have told you before, the surface 1 and surface 5 for wind direction A will be considered as windward wall. Let me show you here. If the wind is blowing in direction A, then wall 1, wall 5, these two walls will be treated as windward wall. So coefficient is 0.85. Using the same equation with GCP value as 0.818, the windward positive pressure comes out to be 6.837 pound per square feet, and for negative it comes out to be 11.76 pound per square feet. Now, as I mentioned before, surface 2 and surface 4 and surface 6, these are the side walls. For side wall, 0.7 is the value of CP. Let me show you over here. Side wall, all values 0.7. So I'm using this 0.7 using the same equation, and my answer comes out to be, so positive pressure is minus 10.598, and for negative the value comes out to be, when I am taking the value of GCP negative, so the value comes out to be minus 5.675. For leeward wall, the length is 80, B is 40, so L upon B is 2, it comes out to be 0.3. Let me show you. Leeward wall 2, 0.3. So all these coefficients are taken from this table. And now for roof pressure, as we discussed, surface 7 and 11, they are the roof, first calculated the roof pressure on surface 7 and 11. These two surfaces are inclined at an angle of 15 degree. So average height comes out to be eave height plus tangent of this. So H comes out to be 12.144, which is H upon L is equals to 0.152. So going back to the table, roof pressure coefficient CP for use with QH, windward side, H upon L is less than 0.25. If the angle theta is 15, so value comes out to be 0.5. And the another value, the minimum value is 0 also. So using the same values over here, CP is 0.5. I calculated P minimum, and for maximum value is taken as 0. So both these pressures on surface 7 and 11 are calculated here. So positive pressure comes out to be when GCPI is taken as positive, the value comes out to be minus 8.273, and when it is taken as negative, it comes out to be minus 3.35. When it is 0, the values are 2.461. Now, for surface 8 and 9, which are parallel to the wind direction, the theta will be 0, and H upon L, the CP value will be 0.9 horizontal distance from windward to H. So let's see this value. So here, when the wind direction, when theta is less than 10 degree, from 0 to h by 2 or h by 2 to h, that means 0 to h, the value of Cp is 0.9 and minus 0.18. So same factor is used over here, minus 0.9 and 0.18. So the pressure on surface 8 and surface 9 when theta is equal to 0 is calculated like this. The pressure comes out to be 12.9 and minus 8, and for minus 1.18 it comes out to be 4.55 and 0.369. And when is h to 2h, the Cp value is 0.5. Let me show you. H to 2h, Cp value is 0.5 and minus 0.18. So now these values are used to calculate the pressure, and for surface 10 which is 0.5, and similarly the overhang area is calculated. For overhang, we have to refer section 27.3.3. Let me show you section 27.3.3. Section 27.3.3, overhang. The positive external pressure on the bottom surface of the windward roof overhang shall be determined using Cp is equal to 0.8. So only one value we have used, Cp is equal to 0.8, and this is the pressure. So this is the wind pressure calculation if the wind is blowing in direction A. Now second, if wind is blowing in direction B, so the only thing will be now the sides will be changed. Otherwise the same table is used over here and it is calculated in the same way. So it is B, C, D, etc. All surfaces should be calculated over here. So once you calculate the pressure on all surfaces, then you can calculate the pressure for component and cladding. In component and cladding, of course, we have to follow chapter 30, which is specifically for component and cladding, and if you remember, the same procedure was used. There were some corner zones, mid zone, etc. So let me go to chapter 27 and let us start to understand how the wind load for component and cladding is calculated. Let me show you chapter 30, which is used for component and cladding. So this is the wind load for component and cladding. Part 1 is low-rise building. So part 1 is of chapter 30 to determine wind pressure on component and cladding of enclosed and partially enclosed low-rise buildings that have roof slope shaped as specified in the applicable figure. The provisions in part 1 are based on the envelope procedure with wind pressure calculated using the specified equation as applicable to each building surface. And here is the procedure given, that the wind pressure should be calculated as per the formula P is equals to QH into GCP minus GCPI, and the values of GCP should be calculated as per figure 30.3-1 for the wall, and for roof etc. it is calculated over here. So let me show you figure 30.3-1. This is the condition. So this is a simple roof, gable. So all values are calculated over here. Let me show you. As specified, that wall studs are 10 feet long and spaced at 16 inch apart. So B of the wall is 16, height is 10, length is equals to 40 feet. It's not CMU wall. So wall effective wind area is determined as per section 26.2, which says that this area should be taken as maximum of H into H by 3 or H into B. So the maximum comes out to be 33.333 per square feet. And the corner zones, the definition of A is equals to minimum of 0.1 L or 0.4 into H. So if we put all these values, the value of A comes out to be 4 feet. Now corner zone 4 and 5. So here we have to let me show you what is the meaning of a zone over here. As per figure 30.3-1, components and cladding, when H is equals to less than or equal to 60 feet, external pressure coefficient GCP for enclosed and partially enclosed buildings are here. So the A, which is defined over here, is shown over here. This is A. Effective wind area is calculated like this, and various zones are defined like this. For example, zone 4 and 5. Zone 4 and 5 means zone 4 is here, zone 5 is at the corner. Zone 4 is here. Now, wind is blowing, say for example, in this direction, which we have considered as A. So for zone 4 and 5, zone 4 and 5, our area is 33.33. So area here is 20, 50, so something will be somewhere here. Now you can see here the value is 1, here the value is 0.8. So for zone 4 and 5, when the area is 33, it comes out to be 0.9, which is almost in the middle. So here we took 0.91 and we calculated the pressure over here. And for negative values, when GCPI is negative, zone 4 and 5, they have different values. So zone 4, this CP comes out to be minus 1.01. So zone 4 is somewhere here, little bit higher, so that's why 1.01. And for zone 5 is almost minus 1.22, little higher than this ordinate 1.2, so 1.22. Now for the roof component, we have to consider the figure given in 30.3-2b, and this is the figure which is applicable for our cases, and these are the graphs which we have followed. The roof pressure, the roof trusses are 32 feet long and spaced at 4 feet. So that means the effective area of the roof will be maximum of 32 into 4 or 32 into 32 by 3. So the roof area comes out to be 341.33 feet squared when angle is 15 degree. So now we are considering zone 1, 2 and 3. These zones are as per ASCE 716. Here are the figure. Zone 1, 2 and 3, which is in the corner. The figure is not very clear. Anyway, so we can use this figure 30.3-2b, and we can take the values as per the graph given over here, and this is the values taken. And the same method is used for zone 2n, 2r and 3, etc., zone 3, etc. All these zones, the overhang area, all are calculated with the same technique. Just as a method of repetition, one can go and check the values and take the values of GCP and put in the formula, and so he will get the positive and negative pressure. Now, very important question. 4 wind directions, A, B, C and D, and there are 12 surfaces here and there. So our calculation means, and for every surface there are 2. So 12 multiplied by 4 is 48, multiplied by 2, one positive, one negative, that means 96 values have been calculated. Fine. So what I will do with all these 96 value? Which load case I should consider? This is very important. Otherwise we will be lost. So far what we have done, we have calculated all the possible wind directions, and because of all possible wind directions, we have calculated the wind pressure on every wall, every part of the roof, even the component and cladding. But in our load combinations, the wind load is considered either in one direction or another direction, or so in which direction we should consider, and what we have to do for all these possible calculations. Here is the possible load combination given. Once you calculate all the load cases which is there for component and cladding, then this is the combination of wind load. That means you should consider first A and B, then A and C, then B and D, and then C and D. So this will be the possible wind load combination, and you should use these wind load combination in your calculation. And whenever you want to design the component and cladding, of course I have shown how to calculate the wind pressure for component and cladding, and you can design that. So hopefully this will clarify the wind load calculation for an irregular shape building. And whenever you have an irregular shape building, you should adopt the same methodology. That means you have to design the building for all the possible wind directions and for all the possible surfaces, and then ultimately you have to define the wind load cases and combine into mutually perpendicular directions. As I have shown just before, take two mutually perpendicular direction at one time, and you can define these four simple load cases. So hopefully this is clear how we define the wind load cases for an irregular shape building. Because the irregular shape building, if you directly use the wind generator for STAD or SAP, etc., maybe you will not get the correct result. So for irregular shape building, better to use this technique, calculate all the wind loads in all possible directions manually and then use it. So thank you. Please do not forget to subscribe my channel, and if you have some comment, your comments are welcome. So let's say goodbye now. Okay, bye.